science video lessons. In the previous class, you learned about magnetic effect of electric current. Can anyone tell me what is magnetic effect of electric current? Yes. A current carrying conductor induces magnetic field around it. This is nothing but magnetic effect of electric current. Very simple. So in this class, we are going to learn one of the important application of magnetic effect of electric current. We'll start the lesson with a simple experiment. Children, now please observe here. Here we have a magnetic needle mounted such a way that it is free to rotate, free to move or rotate in its axis. And a coil of copper wire is wound aligned with the magnetic needle in the north-south direction. So simple device. Now we are going to pass current through the coil and we'll see how the magnetic needle behaves. Okay, so keep observing. I'm going to switch on the illuminator and you just see what happens. Okay, fine. The needle gets deflected. This is what we demonstrated in the previous class. In the previous class, we saw this result. When current is passed through the coil around the magnetic needle deflects. My question here is, what makes the needle deflect? Can anyone tell me? Yes, the current carrying coil loop produces magnetic field along its axis at the center of the loop. Current carrying loop produces magnetic field at the center of the loop. The magnetic needle mounted at the center of the loop such a way that it is free to rotate. So there are two magnetic fields now. One magnetic field is produced by the magnetic needle. The other one is produced by the loop aligned with the magnetic needle. These two magnetic fields, when interact, the magnetic field produced by the loop aligned with the magnetic needle provides a mechanical force on the two arms, north and south poles of the magnetic needle in opposite direction. So these two forces which are acting on the two arms of the magnetic needle are equal but opposite in direction. Hence, the magnetic needle deflects, changes its position. So this principle, this observation is made use in the so-called electric motor. So what is this principle? A current carrying conductor or a magnet placed in another magnetic field experiences a mechanical force. This mechanical force makes the conductor or the magnet move. This is called Fleming's left hand rule. This is the application of magnetic effect of electric current, application of magnetic current, magnetic effect of electric current. So making use of Fleming's left hand rule, we can find the direction of mechanical force acting on a magnet or a conductor in another magnetic field. The magnetic field may be produced by a solenoid or a coil of insulated wire or another magnet itself. A magnet or a current carrying conductor experiences mechanical force in another magnetic field. The direction of the mechanical force acting on the current carrying conductor or the magnet can be found using Fleming's left hand rule. Children, now we are going to learn Fleming's left hand rule in detail. A current carrying conductor or a magnet placed in another magnetic field experiences a mechanical force. The direction of the mechanical force acting on the current carrying conductor or the magnet can be found using Fleming's left hand rule. This so-called Fleming is actually John Ambrose Fleming, a British engineer. He gave us the idea to find the direction of the mechanical force acting on the current carrying conductor. Now, assume that you hold the three fingers of the left hand mutually perpendicular to each other. Three fingers, that is thumb, forefinger and middle finger of the left hand, if held mutually perpendicular to each other, such that the middle finger shows the direction of the current in the conductor. The forefinger shows the direction of the magnetic field. Then the thumb shows the direction of the mechanical force acting on the current carrying conductor. I repeat, if the three fingers, thumb, forefinger and middle finger of the left hand are held mutually perpendicular to each other such that the middle finger shows the direction of the current in the conductor, the forefinger shows the direction of the magnetic field, then the thumb shows the direction of the mechanical force acting on the conductor. Very simple. So, making use of this rule, that is Fleming's left hand rule, you can find the direction in which mechanical force acting on the current carrying conductor. Okay. So, Fleming's left hand rule is also called motor rule. Fleming's left hand rule is also called motor rule, and this class we are going to learn how an electric motor, a DC motor functions. We are going to learn the structure and function of a typical DC motor. Children, the construction and working of a typical DC motor is like this. In a simple DC motor, a coil of insulated copper wire ABCD having several turns. Only one third is shown in this figure, but it will contain several turns. Coil of insulated copper wire ABCD, preferably in rectangular shape. Okay, is placed or mounted between the strong north-south poles of a permanent magnet. Between the strong north-south poles of a permanent magnet. So it is mounted in such a way that this coil of copper wire is free to rotate. Right. The ends of the copper wire, two ends, are connected to two split rings, copper That means what are split rings? A whole copper ring is cut into two parts. Each one is called a split ring. So split ring 1, split ring 2. The ends are connected here. It's soldered here. Okay. There are two carbon brushes R1 and R2. Two carbon brushes R1 and R2 in contact with the split rings. In contact with the split rings. External source of electric current is connected to the brushes through a switch. This is the simple constructional detail of a DC motor. Now we will see how it works. When the external battery connected to the brushes is switched on, current from the positive pole of the battery or battery eliminator reaches brush 1. From there, through split ring 1 in this direction A, B, C, D and back to split ring S2 and through brush B2 it reaches the battery. So one cycle is completed. One cycle is completed. From battery to brush 1, from brush 1 to split ring 1, from there in the direction A, B, C, D in the coil, back to the battery through S2, split ring 2, brush 2 and the cycle is completed. This is the way the current flows in the armature, in this coil. It is also called armature. Now we will make use of Fleming's left hand rule. Fleming's left hand rule. Now look here. This is the direction of the magnetic field. Magnetic field is from north to south. So this is the direction of the magnetic field. So if you apply Fleming's left hand rule, you can see that a mechanical force acting on the arm AB, outward it is. The direction of the mechanical force acting on this arm AB of the coil is outward. At the same time, the mechanical force acting on the arm CD of the coil will be inward. So the two forces are equal and opposite. Equal and opposite. Hence, this coil makes half a turn. 180 degree it rotates. 180 degree it rotates. That is called the half cycle of the armature. It completes half cycle, that is 180 degree rotation. At 180 degree rotation, just look here, D comes here, this is C now, DC, BA. S2, this S2 becomes, S1 becomes S2 and this becomes S1. Brushes are stationary, it won't change. Now look here, the current is flowing in the external circuit in the same direction. In the second half of the half cycle of the armature. Reaches B1, from B1 through S2, it flows in the coil in the direction BCBA. Through S1 and B2, the current flows back to the battery and the cycle is completed. So, again, applying Fleming's left hand rule, the arm CD gets pushed outward this direction and arm AB is pushed inward. So the armature coil makes the second 180 degree rotation. So both the half cycles together, the armature coil, as long as the current flows through the coil, the armature same direction. The armature coil, this coil keep rotating in the same direction. The axle of the coil is a strong metal rod. Axle of the coil can be connected to any machine, and the mechanical force generated can be used to run the machine. This is what a motor does. So, what is a motor? What is a motor? Motor is a device which converts electrical energy into mechanical energy. What is a motor? Motor is a device which converts electrical energy into mechanical energy. Mechanical in sense, it may be rotation, it may be sliding motion. So here I explained about rotation. Okay, so electrical energy is converted into mechanical energy, and that mechanical energy can be utilized to run machineries, small and big. Small and big. At home you have, say for example, CD player, wherein you see small motor, miniature motor. Electrical energy is used to run that motor, and that motor spins the compact disc. In the industries, huge machineries are run using electrical motor. Your ceiling fan, your washing machine, your mixer grinder, all these things contain electric motor. So, children, I hope you understood the construction and working of a simple electric motor. DC motor. We made use of direct current. We are using direct current, so it is called DC motor. We are not going to deal with the AC motor. The construction and the working of AC motor is quite different. So when you go to higher classes, you will learn about it. Understand? Now we will see, this is theory. Theory you understood. Now we will see whether it works. The practical also works the same way as that of the theory. We will do some simple demonstration experiment. Okay. This is the demonstration model of a simple electric motor. So, if you observe carefully, you can see the coil of copper wire. We have instead of one coil, here we have 3 coils. Just to increase the efficiency. Okay, we have 3 coils. So this combination of coils called the armature is mounted between 2 magnetic poles, north pole and south pole. You see, here inside there is a magnetic pole, and this side also there is a magnetic pole. So the coil or the armature is mounted between the magnetic poles. Now, at one end of the axis, you have split rings. 1, 2, 3. Instead of 2 split rings, since we have 3 coils here, for 1 coil you get 2 split rings. For 3 coils, it is adjusted such that we have 3 split rings. 1 ring is cut into 3 equal parts, and each one is fixed on this axis, on this axle of the armature. You can see the split rings also. Got it? Now, connected to the split rings, you can see 2 brushes. Instead of carbon brushes, here brass strips are used. Instead of carbon brushes, brass strips are used. The brass strips are connected to the external terminals, positive and negative. Positive and negative. Okay. So that is the constructional aspect. Switch on the battery. We'll see. Okay. It's working now. You see? the armature is rotating and the motor is spinning. You see, it's spinning very fast. So this is how electrical energy is transformed into mechanical energy by making use of a motor. Children, now I am going to display the parts of a commercial DC motor. Commercial DC motor. Now see here, this is the armature of a motor. See, in the theoretical part you saw only one coil, you see, A, B, C, D, one coil. In the demonstration model you saw 3 coils. Here you have many coils. Nearly 9 to 12 coils are wound on the same axis and the armature coil is made. The armature coil is made by winding 9 to 12 coils on the same axis. And instead of 2 or 3 split rings, you have many split rings. If there are 9 coils, you will be having 18 split rings. 18 split rings. For one coil, 2 rings. At the rate of 2 rings, split rings per coil, you will have 18 split rings here. If there are 12 coils, you will be having 24 pieces of the copper or brass ring. It's copper ring. It cut into so many pieces. Maybe 12 pieces. I mean, for 9 it is 18 pieces, or for 12 it is 24 pieces. Okay. So ends of the copper, ends of the coil are connected to the split rings. I told you about carbon brushes. These are the carbon brushes. You have 2 brushes to be connected like this in the mount. 2 brushes are in contact with the split rings. See, this is the mount for the split ring, I mean carbon brush, mount for the carbon brush. So this mount comes in contact with the carbon brushes, comes in contact with when this mount is placed in the device. And here you have 2 magnetic poles. See, this is one magnetic pole, this is another magnetic pole. How strong it is, you see. See, it's so strong it is. So, this armature is mounted between 2 magnetic poles. Understand? So, it is mounted actually using ball bearings. Here this side it will be, and this side one more cap will be there. So it will be free, the armature will be free to rotate. Understand? Free to rotate. So you have seen the parts of a commercial DC motor. This is, all of you would have seen this in electronic appliances. You see this type of small motors. These are called miniature motors. This is a commercial miniature motor. Same constructional principle. Inside you will be having a coil of copper wire called the armature and split rings and carbon brushes also. Only thing is, it is very small in size, so it's called miniature motor. This is another motor. This is not a DC motor, it's an AC motor. AC motor. 220 volts AC is supplied here and it keeps rotating like this, spinning like this. You understand? I'll just show you. What is it now? Because it is hexagonal screw, I don't have the hexagonal key to open it, unscrew it. Otherwise I have shown. Inside you see only one coil and no magnet, nothing. This part, it is called the rotor, which is rotating, and one field coil that is stationary, it is called stator. One stator and one rotor, AC motor it is. This is directly connected to 220 volts source, okay. I am going to switch it on. You see, this type of motor you can see in your table fan, in your table fans. The table fans, what table fan or pedestal fan, the fans which you use consist of this type of motor. The ceiling fans, the motor of the ceiling fans also work in the same way, but the constructional aspect is little different. Constructional aspect is little different. If you go to a motor winding shop or a mixer grinder repair shop, you can see the variety of motors, and you can also the technician there and get information how the motor works and things like that. So those who are interested may go to a motor winding shop or a mixer grinder or any other electrical shop. They will show you the details and variety of motors and how it functions. Okay. A quick recap. First point is motor rule or Fleming's left-hand rule. The mechanical force acting on a current carrying conductor can be found using Fleming's left-hand rule. If the three fingers, middle finger, forefinger and thumb of the left hand are held mutually perpendicular to each other, such that the middle finger shows the direction of the current in the conductor, the forefinger showing the direction of the magnetic field, then the thumb shows the direction of the mechanical force acting on the conductor. That's very important thing. It is called Fleming's left hand rule or motor rule. You have to learn this rule. Okay. Next is construction of DC motor, the application of Fleming's left hand rule or the application of magnetic effect of electric current. Here we learned the construction and working of a simple DC motor. A coil of insulated copper wire ABCD is mounted between the strong NS north-south poles of a magnet. The ends of the coil are connected to two split rings S1 and S2. There are two carbon brushes B1 and B2 in contact with the split rings. External source of current is connected to the carbon brushes. So when circuit is switched on, current flows in the direction, first in the direction ABCD, and the mechanical force acting on the conductor of the coil will be outward. On the arm AB it will be outward, and on the arm CD it will be inward, and the armature makes 180-degree rotation. In the second half, the current in the coil, in the arm DC, it will be outward, and in the arm AB, it will be inward. Again, the coil makes the second half rotation. Thus, a cycle is completed, and as long as the current flows through the armature coil, the coil keeps rotating in this direction. In this direction. Thus, electrical energy gets converted into mechanical energy. So a motor is a device which converts electrical energy into mechanical energy. What are the applications of electric motor? Small and big machines, electrical machines wherein rotation or sliding, rotational movement or sliding movement is taking place. It has to contain an electric motor. So small devices like your computer, hard disk, your CD player, then the machines like say for example kitchen machines like mixer grinder, wet grinder, even your microwave oven, the base of the microwave oven, when you have a thick glass plate, it keep rotating, you know. That means to say there is a motor inside. There is a motor inside. Your washing machine spins, so there is a electric motor inside. Your ceiling fan, there is a electric motor. So any electrical device which spins or slides, there is a electric motor. So uses of electric motor, or they may ask you, write 4 gadgets wherein electric motor is used. You have to think and write. Don't write electric iron. Istilpettige. Electric iron is not a device wherein electric motor is used. So you have to think and write. Electric heater doesn't use an electric motor. So that is heating device. Electric motor is not a heating device. Keep the point in mind. So uses of electric motor, you know. Now note down the home assignment. Children, you have 4 questions here for your homework. First one, state Fleming's left hand rule. This is also called the motor rule. Second question is, what is an electric motor? Third one, draw the neat and labeled diagram of DC motor. Explain the construction and working. Name 4 domestic appliances wherein electric motor is used. So answer these questions. Had you listened and observed my class, you can very well answer these questions, and you have your textbook. Refer the textbook also and answer the questions beautifully. That's all for now. We will continue with this chapter in the next class. Thank you. Bye-bye.